what we're going to talk about is taking the derivative in the integral of e to the x, which is a logical follow-up to natural log, because they are inverses of each other. If you find the inverse of y equals ln x, remember that that's the same thing as y equals log base e of x. And how do you find the inverse of an equation? Yeah, switch the x's and the y's. Good. So it would be x equals log base e of y. Now, can anybody remember how to switch that logarithmic equation into an exponent? It's e to the x equals y. Good. If you'll recall, here's the graph of ln x. And hopefully you remember that this is the graph of e to the x. And inverse functions are reflections across the line y equals x. So if you were to reflect your natural log graph across the line y equals x, you would get your e to the x graph. What is the domain of e to the x? All real numbers, right. And what's the range? Good, 0 to infinity, which is just the opposite of the domain and range of ln x. The domain of ln x was 0 to infinity, and the range was negative infinity to infinity, which makes sense if you're just flipping your x's and y's. That's kind of a shortcut to saying you're flipping the domain and the range, or switching that around. All right, so when we talk about e to the x, it's continuous, it's increasing, and it's one-to-one on its entire domain. You can see from the graph that it is increasing and it's continuous. One-to-one means it passes both the vertical line test and the horizontal line test. And what is the concavity of the graph? Up. Okay. What's the limit as x approaches infinity of e to the x? Or does that say infinity or negative infinity? Okay. The first one is negative infinity. The limit as x approaches negative infinity. It's 0. And the limit as x approaches infinity is infinity. Or does not exist, but I like the infinity better. A limit that approaches, in order for a limit to exist, it has to approach a specific number. So because it's not approaching a specific number, it doesn't exist. All right, let's just do a quick review on solving equations using natural log and e to the x. All right, if we have the equation 7 equals e to the x plus 1, if you start with an exponential equation, you can take the natural log of both sides. Just help you solve for it. So take the natural log of both sides. So on the left, we have the natural log of 7. Now, the natural log of e to the x plus 1 power. Okay, it's x plus 1 times ln e. Is that what somebody said?
Yeah.
It does kind of end up canceling, because what right here, and I thought this was what somebody was trying to do, is the exponent of x plus 1 can come down in front of the natural log of e. So that's what I did. And then what is the natural log of e? 1. So we really just have x plus 1 equals ln 7. So x would equal the natural log of 7 minus 1. And then you could type that into your calculator. There is a property that the natural log of e to a power just equals that power. So I think some of you recognize that the natural log of e to the x plus 1 just equaled x plus 1. Brian? Yeah. This is kind of, I'm not really going to test you over this. This is just kind of a review of isolating an x if you need to. But this would be considered an exact value, and I think that's even easier to deal with than using your calculator. All right, number 2. If you start with a natural log, then we can use exponents to help us here. Is there a way to rewrite this in exponential form? E to the 5th equals 2x minus 3. Yeah. There's this property, or the definition of a logarithm is log base a of x equals y if and only if a to the y power equals x. So you can take the base of the logarithm to the power of the thing that's all by itself, and then that equals the argument. And then if we want to solve for x, it would just be e to the 5th plus 3 all divided by 2. Okay, the derivative of the natural exponential function, which is e to the x. The derivative of e to the x actually equals e to the x. Okay? Kind of weird. Or if you've got something other than plain old x as your exponent, the derivative of e to the u is e to the u times the derivative of u. Huh? Okay. When we took the derivative of natural log, it's 1 over the argument times the derivative of the argument. Well, the derivative of e to a power is e to that same power times the derivative of that power, or the derivative of that exponent. Yeah, we're just using the chain rule here. The derivative of e to the u is e to the u, and then times the derivative of u with respect to x. That's the du dx. So geometrically speaking, the slope of the graph of y equals e to the x at any point is equal to the y value at that point. That's why it's a really special function, because the slope of the graph of e to the x is always equal to the y value at that specific point. That's why the derivative is the same as the original function. All right. You're going to throw yourself a party every time you have to take the derivative of e to the x because it's so easy. You're going to be so excited. Yeah, woohoo. All right, so y equals e to the 3x minus 5. Yeah. So the derivative is just e to the exact same power, and then times the derivative of that exponent. What's the derivative of 3x minus 5? 3. You're done. Okay. You don't need the dx because y, the derivative of y is either y prime or dy dx. So either way. All right, on 4, I would personally rewrite this as y equals e to the negative 7x to the negative 2. Everybody okay with that? So therefore, the derivative would be what? E to the negative 7x to the negative 2 times 14x to the negative 3. Good. So it's just e to the exact same power times the derivative of that exponent. It is so easy. Okay, find the relative extrema of x e to the x. Okay, we do have to use the product rule. And to find the relative extrema, I need the critical points, which the critical points are where the derivative equals or is undefined, right? 0 or undefined. Okay, so first off, to find f prime, we do have to use the product rule. So the derivative of the first times the second would just be e to the x plus the first times the derivative of the second. What's the derivative of e to the x? E to the x. Is there any place that that derivative is going to be undefined? If x is 0, I'd have e to the 0, which what's e to the 0? 1. Yeah. The domain of e to the x is all real numbers, so you don't have a problem there, and then you don't have any x's in the denominator, so the derivative will never be undefined. All right, how do you want to solve this equal to 0? Okay, factor out an e to the x, and you're left with Okay, so e to the x equals 0 and x equals negative 1. What value of x will make e to the x equals 0? Yep. Okay, there's the graph of e to the x. And you have a horizontal asymptote along the x-axis. So e to the x will never equal 0. So it's basically an extraneous solution. So our only critical point is x equals negative 1. And how do we tell if that is a min or a max? Plug it in the number line. Am I going to plug it into f prime or f? Right, f prime. Okay, so if I plug in a, say, negative 2, I would say plug it into this part right here. E to the negative 2, is that positive or negative? Positive. E to a power will always be positive. Times a negative is a negative. And if you plug in 0, you're going to get 1 times 1, which is positive. So we have a relative min at negative 1, comma, what's the y value? Yep, negative 1 over e. Or negative e to the negative 1. Because, what's my justification? Yeah. I got the negative 1 over e by plugging negative 1 back up into the original equation, the f. So negative 1 times e to the negative 1. And instead of doing e to the negative 1, she just brought that down to the bottom. Okay, number 6. For 1970 to 1990, the number of medical doctors in the U.S. can be modeled by y equals blah, 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 where t equals 0 represents 1970. At what rate was the number of MDs changing in 1988? So what do I want to do? Take the derivative and plug in 18. Yeah, so I'm trying to find y prime of 18. I would obviously let you use your calculator on this because it would be a nightmare not to. You take the derivative and you type in the 34800 000, and then e to the, so you do diamond, e to the 0.033 666x. Okay, anytime you take a derivative, you have to do comma x and close your parenthesis. And then we want the calculator to evaluate that derivative when x equals 18. So you do the bar x equals 18. And then diamond enter. 21,475. Okay. So what does that number really mean? That in 1988, what's happening? It's the rate of what? Change of MDs. So at that, in 1988, there are 21,000 more doctors than there were the previous year. So that rate is growing pretty fast.